Okay, class. So we will now go to industrial crystallization. So again, the focus here is a little bit on the supersaturation of a given solution, and then next would be the design of the crystallizer and the material balance involved in the crystallizer. Now, when you'd like to determine the degree of supersaturation, let's say represented by delta C here, well, C represents the concentration of the solution containing the solid. That would be the difference of the concentration of the solution and its equilibrium saturation value. The saturation value at equilibrium is already the maximum amount of solid that your solution can contain, and no further amount of solids could be dissolved in it already. And that's the start already of crystallization, this particular equilibrium saturation value. Now, as to the supersaturation ratio, you are still dealing with these two C's, the C and the C asterisk. However, it's the ratio of the two that you are measuring in here. So it could be the degree of supersaturation, how much has the concentration deviated from the equilibrium saturation value, and its ratio in terms of the equilibrium saturation value for supersaturation ratio. Now, as to relative supersaturation, we are still using the C's in the previous slide, but this time 1C, and that's the concentration at equilibrium, is used as the basis in determining how much has the degree of separation compared to the supersaturation, or rather the concentration value at equilibrium. How much has the degree of supersaturation uh, is compared to the solution concentration at equilibrium. Now, this one could be a simple case of S minus 1, which is the supersaturation ratio minus 1. Now, speaking of concentrations here, there are two ways in which we could express concentration of our solution in the topic of crystallization. That would be the mass of anhydrate, meaning the pure solid without the water, divided by the mass of the solvent, and that is water. Or it could be the mass of hydrate, that is the sum already of the mass of the dry solid and that of the water over the mass of water. So the most commonly used method of using concentration is the mass of anhydrate, and that is that of the dry solid only over the mass of the solvent. But it could also be like this. It could also express concentration in terms of the total mass of the dry solid and the solvent over the mass of the solvent. And this choice of using concentrations representation affects the values of the S and the relative supersaturation. Now, let's say we will have to draw our crystallizer here in the form of a box. So the water that is vaporized in the process of crystallization is represented by V with its corresponding enthalpy. The feed is represented as F and its corresponding parameters here, temperature, enthalpy, and mass fraction of the solid in the feed. And we have the magma. The magma is composed of the liquor and the crystals, which we later on separate with the main objective of taking the crystals out from, or producing the crystals out of the original feed. So you have the parameters as well of the magma with the subscript M, for the liquor with the subscript L, and for the crystals with the subscript C. So this is how we represent our crystallizer, a simple representation of our crystallizer. It could be seen here that our feed, the mass of our feed, should be equal, of course, to the mass of the vapor and the mass of the magma, which is equal to that of the liquor and the crystals. Now, material balance equation for this can be read through in your John Copley's book or even in McCabe. Now, a very important also mode of checking the degree of, let's say, recovery of crystals from a given solution or feed in which is to be produced from is what we call as the yield of crystals. So the yield of crystals produced by a given degree of cooling can be estimated from the concentration of the initial solution and the solubility at the final concentration. Speaking class of the solubility at the final concentration, this is also in the form of a concentration. So meaning we don't have another representation or separate representation for solubility of the final at the final temperature, but rather we have concentration also at the final temperature, both of which represent the same thing. Only that it was just asked or represented here in the form of the term solubility, but actually it's also concentration. Now, going back to the yield of crystals, so it can be estimated from the concentration initially of your solution and the final concentration, allowing for any evaporation if there is evaporation, and by making solvent and solute balances. So for us to be able to determine the yield crystals, we will make material balance and we can do also solvent balance. So material balance is in the terms of the solute, is in terms of the solute or the solid, and solvent balance most of the time is in terms of water. Now, the formula that you are seeing here in terms of the yield for an aqueous solution, meaning your solvent is water, for a particular solution containing crystals, it's a different formula than what is available in Janku Place, and it's the formula that I've been using ever since when I discussed crystallization. It's coming from Colson. But if you intend to really determine the yield crystal based on the simple material balance equation available in your textbook, you may do so. But let's say you're going to use the formula that is indicated on the slide in terms of the yield of crystals from an aqueous solution. So in the formula that you see here, the W's represent masses. So masses, initial and final masses of the solvent in the liquor. So take note of the solvent, not of the solute. Y is the yield of the crystals. R is the ratio of the molecular mass of the hydrate, and that is molecular mass of the crystal with the water, and the molecular mass of the dry solid. Molecular mass of the hydrate and the molecular mass of the dry solid or the anhydrous salt. And the E is the ratio of the mass. So if R is molecular mass ratio, the E is mass ratio. Mass of the solvent that was vaporized, that is if there is evaporation, over the mass of solvent in the initial solution. In some problem, this E is 0 because we don't have vaporized amount of solvent. The process of crystallization in this case is through vacuum crystallization. So we don't have considerable amount of water vaporized. But if there is, the problem was really specify if there is an amount of water evaporated during the process of crystallization. So this is how we define the E, the R, the W's, and of course the Y based on this particular formula. The C still represents concentration. C1 is initial, C2 is final. Now, if the E is not given in the problem, the ratio of the mass of the solvent that was evaporated to the mass of the solvent in the initial solution, it could be solved using this particular formula. So this particular formula, however, has an added requirement on it because in some problems, a case of simple material balance as illustrated in your textbook, Janku, please, will not work. There are problems that give you the amount of heat, which is the Q. So in this case, there's a need for us to have another formula that we could use in determining the E, aside from this simple definition of the E, if it is not, as I said, available. the information is not available in the problem. So this is how we determine it. So in this formula, your lambda is the latent heat of evaporation of the solvent. So again, water. Q is the heat of crystallization of the product. And since it's a constant for a particular solid, the problem should be giving this. Then the T sub 1 is the initial temperature of the solution in Kelvin. Same thing with the T sub 2 in Kelvin, but this time it's the final temperature. And Cp is the specific heat of the solution of water and your solid. Now, the common problem involved in crystallization is in the design of the most commonly utilized industrial crystallizer, which is the mixed suspension, mixed product removal type of crystallizer, or what we call the MSMPR type of crystallizer. And this is the common type of crystallizer that is often coming out of the board exam. So that is why emphasis was given on this when it was discussed in heat and mass transfer. So in here, when you are to determine for a particular MSMPR the solid content of the magma, you are to use this particular formula, or shall we say, if it's not as in the form of the solid content of the magma, it would be as in the form of what is the magma density. So in here, you'll be using this particular values, which should be given as well by the problem. So we have the volumetric shape factor, the crystal density, the nucleation rate, the growth rate, and the drawdown time. This term drawdown time is actually residence time in crystallization. So it's just how long did your magma stay inside your crystallizer for you to be able to separate the formed crystal from the liquor, from the, shall we say, the spent liquor, because you have already taken out the crystals. So drawdown time, residence time in crystallization. So that is why the subscript is also T sub R. If we follow the formula, we'll be able to determine the magma density, which is actually the measure of its solid content. Now, in that particular formula in here, you have nucleation rate, and it's also found in this particular formula, the nucleation rate. And what does this particular formula determines or calculates? So this one calculates the number of crystal per unit size per unit volume of the system. It's a hypothetical way of determining how many crystals of a particular size per unit volume is present in your magma. And this is the formula for that. You need the crystal size, you need the population density in here, just like in this particular formula. That's the nucleation rate. In here is the population density of the nuclei. And you have here the growth rate and the drawdown time, which is also the residence time. If the problem does not give you parameters that allows you to use this particular formula, I'm certain that the problem will not also asking you for the population of the crystals or the population density of the crystals inside your crystallizer. But should it be asked, then these other parameters here in this formula should be given, because as I said, we don't have a particular chart to get them from. We don't get them from a chart. We don't get them from a table. Otherwise provided, then we can use this particular formula whenever the need arises. Now, the problems for crystallization is so varied that I have decided to share with you the chemical engineering series, which is a compilation of all lectures and solved problems in crystallization. This will help you greatly in terms of exposing you to varied types of problems, solved problems in industrial crystallization, and the varied way of representing the parameters in the formulas that will be later on used. If you notice, class, the problems here are very lengthy. They have a lot of variables to consider, but it's worth preparing. So we did not go into the details of this during HMT, considering the time that we have in solving such problems. So these are the solved problems under crystallization that you can really use and later on refer to when you process your problem sets. So this would be the end of the short topic on industrial crystallization.